Okay. Can you see my screen, guys? Okay. So just remember that this is the R signal in here, just like this one. Okay. And so how can we obtain the parameters of these terms? Firstly, we have used the step info function to get the response characteristics. Okay. First of all, the info can be defined as the step info function, which is given with what, the tf1. Okay. If I run this code, and then this info gives us or generates to the what, the struct with or the in terms of what, the rise time, transient time, settling mean, settling max, overshoot value, undershoot, peak, and peak time. Okay. And so this step function analyzes the whole the results based on the analytical or the signal information, and then this gives us the parameters of the R system, just like this one. But how can we obtain this value based on the what, the R nodes or the R equations? Okay, this is the case of this lesson. But first of all, we need to write this value f printf settling time f seconds new line info dot can be reach settling time, just like this one. And so we need to write also rise time. Okay, rise time, and also we need to give the overshoot value. It's the overshoot. Okay, and also we need to give the peak time. Okay, and also we need to give the steady state values. Okay, this is equals to the what in the calculation we have divided by 2 and settling max plus info settling mean. Okay, this is the values of these terms, because in the settling time we reach the final values of the what, 98%. Okay, and so which means that if we use the settling max value and settling mean value, just like this one, and so we can obtain the what, the settling max, for example this one, and settling mean, for example this one, and then we can take an average values of the settling max and mean value with the divide by the 2, and then this yields us the steady state values of our term. Okay, so just like this one. Okay, these are the parameters, but how can we calculate these terms by hand? So estimate from the response, output, and time. Okay. Firstly, we need to analyze the steady state value. In order to calculate the steady state value, we need to take the mean value of the last seconds or the some periods. Okay, and steady state value can be calculated correctly is that the response output 90 to 110. This is the mean value. It's the average values of what the response output. Okay, because at the last case we have the correct steady state, but we need to take the at least 20 measurement to calculate this value. In order to what? In order to more approximate the correct values of the R terms. Okay, we can say that these terms can be used as this one. Okay, after that we should look at this function. It's in here. Okay, firstly you need to understand that our steady state values should be equalized in the second order form, just like this one. Wn is the natural frequency of the R system. Okay, and so this R system yields us to what the final values of these terms. Okay, and so this steady state value is assigned with what? With this value. Okay, and then Wn can be approximated with this calculation, 1 divided by steady state value, because the Wn is R, or the square form of these terms is equals to the what? Steady state value. But we need to take a square to find this term with the what? 1 divided by steady state value. This is the calculation of the natural frequency of these terms, because this response yields us to what? To this case. Underdamped response must be equalized to these terms, just like this one. Okay, and so this Vwn square must be equals to the steady state value. Okay, because we equalize these terms to the 1, and so this 1 divided by Wn square is equals to steady state value. Okay, or in another term, SS is equal to what? 1 divided by Wn square. Okay, and then we can take the Wn is equals to what? SQRT SS. This is the formulation of the Wn. Okay, so for the settling time calculation, we should check the absolute error values. How we can define the settling time in here? Just like this one, the Ts is equals to the 4 divided by zeta dot omega n. We can use this formulation, but if you have any data in your response, and then you can search to to this condition, 0.02 or 0.98 CF value, because we have the last steady state value of our system, and so the last steady state values multiplied with the 98%, which is equals to the settling time. Okay, and so we can assign the end in this in here, just like this one. The length of the response output whole values can be given in here. Okay, and then settling time value can be initialized with the 0, and we can search to hold in this, just like this one, greater than 0. This end in this returns to the length of the response output for the whole of the time, which means that we have the 110 values, or this value kept the values of the 110. Okay, and after that we can define to the R error signal in here, just like this one, absolute value, response output, and in this one minus steady state value divided by steady state value. Okay, these are the solution for the error, because if we have the response output at the end of the index of these terms, just like this one, and so we subtract the steady state value, and so we will have the what error between this response and the steady state value. And so if we divide the steady state value, we get the percentage rate of these terms. Okay, and so if the error greater than 0.02 and settling time value can be assigned to what the response, in this case time, and in this. Okay, and after that we should give the break, because we start hold the search at the end of the response output, because we know that the settling time should be given at this location, and then we search or calculate the whole error values in here just like this one, and then the error if it's greater than 0.02, and then we will have the settling time, the first settling time value in here. Okay, and so the end, and also at each case if you don't have find this value, and in this must be diminished at this time with the 1 value. Okay, and so if I run this code, and then I will show this graph. At the beginning of this while loop, we will add these locations just like this one, and so at each iteration we search the parameters at the left hand of this signal just like this one, but we search the 0.02 error value at the percentage to find out what the first settling time. And so if the error is greater than 0.02, and then we will say that this must be equal to what the settling time value, because at this case, for example, 1%, 1.1, 1.2, 1.3, 1.4, 1.5, but at each case we will reach what a 2% error value, and so this is assigned with these algorithms. Okay, so this is how we can find the R steady state response and the settling time values. Okay, so how can we find out the zeta and overshoot values in here? The overshoot values can easily be calculated with the maximum values of the response output, right? Minus steady state value is the steady state value, right? And we can divide the whole this final value, which is equals to the steady state value times 100. Okay, this is the OS values of our terms, and after that we can find the zeta based on these informations, right? The zeta is equals to 4 divided by ts time omega n. Okay, and so this zeta can be equalized with the 4 divided by settling time value times wn. Okay, so these are parameters for whole given responses. Okay, and so how can we define or write the whole values in here just like this one? For example, the steady state value can be write the system parameters just like this one, steady state value, setting time value, and OS value can be written just like this one. Okay, and so if I run this code, and then we will have these parameters. Firstly, steady state value in the Matlab formulation is equal to the 0.12, but in this case, or in our case, we calculate at the 0.11. Okay, this is so close. between the two of them, okay? And so hover should value is calculated what the 32.93, and so this is the exact representation of these terms, okay? This is also correct. And the settling time is equals to what? 3.70, which is equal to what? 3.6697, okay? And so this is also so close for this case, okay? And so what do we learn about these things? If we have any data coming from the outside or the real-time application, we can design our Matlab response based on these informations, okay? And so how can we do that? To see that, if we have the zeta and the omega n value, and then we can write our own transfer function. It's given in here. Num2 is equal to the 1, okay? And then 2 is equals to the what? 1, and 2 zeta dot wn and wn over square, okay? And so where is this coming from? This notion tf num2 then 2 can be written in here just like this one. But where is it coming from? This equation coming from in these terms, the second order response system, wn square divided by s square plus 2 zeta omega n s plus wn square, okay? And so if we have or obtain the wn value and the zeta value, we can build our estimated transfer function based on this information. And so this transfer function is built using with the what? With the real-time data, time response, and our amplitude response. For example, this could be a motor velocity or the motor position value, or the robot arm position value, or the heat value, or the voltage value, or the current value. It doesn't matter the terms or the variable type. Only we will deal with the what? The mathematical values or the plotting values, and so we can set or build our transfer function based on this information. This is called the estimation of the second order system response, okay? And so how can we compare these two results in here? Figure the step tf1 10 and hold on step tf2 10 and grid on and legend show can be written in here, okay? And so if I run this code and then the tf1 is the what? Is the real one, but the tf2 is our estimated results coming from this data, okay? And so we can utilize this estimated form of the second order system in order to what? In order to converge the real-time results based on this information. This is a huge advantage of the what? The second order system and using the transfer function domain in our real application system. For example, if you want to control the motor system, and then you will take a data, time response, and the motor velocity value, and then you can use this data on the what? The Matlab plot, and then you can utilize these codes in here just like this one, and then we will have the what? The exact representation of this DC motor in the what? In the linear domain. And then we will use this estimated transfer function to what? To control our motor, even if it is a real implemented motor dynamics in the real life application, okay? This is why we need to utilize the linearized and the transfer function domain in the what? In control system theory, okay? Any question about these things? You don't have any question? Okay. And so we will continue with what? With the stability examples in here. Okay. Okay. Just remember the previous lesson. We have talked about or solved the stability range problem. For example, if we have the sims S and K value in here, and we can define the G, K times S plus 5 and divided by S times S plus 10. Okay? Just remember that we solved this problem in the what in by hand. Okay? And after that, the transfer function or the collective transfer function is assigned with what? The G divided by 1 plus G. Okay? That's a closed form for the what? For this range. Just remember that in order to guarantee to the stability of the time or the frequency response of this system, we will select the what? Select the poles at the left hand side of the what? At the S domain. Okay? And so we can write this function or the transfer function with the collection form of the S, just like this one, and then we will have this transfer function in the closed domain, just like this one. And so we will look or examine whole the result based on the this what the denominator part of these things, which is equals to the what? The characteristic equation, right? And so how can we analyze this system? Firstly, you may use the what? The pretty collect function or simplify function in here, just like this one. Roots of the what are parameter 1, k plus 10, and 5 times k can be assigned in here because it are the parameters of these terms. And so this function returns to the what? The root values of the what? R system, just like this one. Okay, and so these are two roots coming from this transfer function or the closed loop time domain system. Okay, and so we will guarantee that these two roots must be equal or the smaller than the 0 or the negative values. Okay, and so how can we check these values in here? First of all, in order to utilize these terms, we can assign the 100, 1 and 100 values in here. This is a branch of the what R array to begin with what 100 minus 100 value up to what 100 at the step rate of the 1. Okay, and so we search the whole k parameters in here, just like this one, and then we can find the stable k values in here. Okay, and after that the S1 is assigned with what? The minus 5 minus k dot 2 plus sqrt form of the k square 100. Okay, and divide by 2. Okay, and S2 is the R another term in here, minus 5 k dot divide by 2 minus sqrt k q plus 100 divide by 2. Okay, where is coming from? These terms are coming from these solutions. Okay, we will write it just like this one. Okay, and so this dot operator is the array multiplication. Okay, so we have S1 and S2 for the k region. Okay, and then what? K stable is an empty array in here, just like this one, for I is equal to the 1 at the rate of 1 and length of the what? The k. Okay, and so we had 200 values to be searched in this space. Okay, and so and then what? if s1 I smaller than 0 and s2 I smaller than 0, which is our condition, the stability condition, right? And k stable value I1 is assigned with what? A k I, right? This is the stable k, and so we put this stable k into what? K stable array, right? After that, if we have this information, and then we can write in these terms in here, just like this one. The k stable minimum value is equals to what? The mean k stable, right? Or k stable maximum value is equals to what? The k stable max. Okay, this is the direct solution of the what? Of our domain. Okay, and so if I run this code and then the k stable mean, in case I'm in an empty space, I'm sorry, 1.1 ki si, I'm sorry guys. Okay. Okay, this is the correct solution of the R4. Okay, I'm sorry about the length, because the k stable is 0 length, and so this is equals to k stable, which is going to 0, and so this for loop does not run at this code, but I corrected in this place. So we have k stable mean in terms of what? The 0 values. Okay, for example, if I choose the minus 1000th value, the same results is given in here. Or we can increase the values of the positive terms in here, just like this one, and then the k stable max is increased, which means that we have a branch for the k stable value in here with the range of the 0 to infinity value. We can test our algorithm or the transfer function or the closed loop transfer function in order to what? In order to provide the which range of the k are stable for a given transfer function domain. This is the basic utilization of the what of the R response in here. Okay, so this is the first place of the what? The stability range problem. Okay, in the second place we have talked about the stability in time domain in the previous weeks. Okay, for example, if I define the A matrix in here, just like this one, 0 and 1 and -2 -3. Okay, and so how can we find out to what this matrix is stable or not? Just remember that in the state space form, x dot is equal to the A times x plus b times u. B times u coming from the outside to the external world, and so this could not be evaluated for the what? For the stability problem, because if you want to stabilize the system, this u is changed or updated, which is what? The control theory, right? And so in order to check out the stability of the time response or the time domain system, and so we just look only the what? The x dot is equal to the a times x. Okay, and so how can we analyze this system? We can use the eigenvalue or the a function in here, just like this one. If I use this function in here, and so -1 and -2 are given in here, which means that these two values are the roots or the characteristic equation roots. Okay, and so if this value are smaller than 0, then we can say that this system is stable. Okay, but for example, if I change the 100 values in here, just like this one, it's also stable. Or 1000 value is also stable. Or 10,000 is also stable, right? Or 20 value in here is also stable. And also this is stable, but this stability range creates two imaginary parts, okay? And so only the real parts are important for checking the stability of the system. For example, this is a plus term, but this is the I value, so the imaginary value. Imaginary values cannot affect to stability of the time domain system. Just we need to look at to what the real part of this system. But if I choose this the positive value, and so we have the 10 and minus 20 value, which means that we have one unstable pole, and this leads us to what this system is unstable. Okay, we can check our system parameters based on these informations. Okay, any question? Okay.